What's up, everyone? Sam here from byte.com, and in this video I'm going to show you how to implement the longest palindromic substring problem. So this is a really popular interview question as well, and we're going to dig into it right after the intro. And if you haven't already, make sure that you hit that subscribe button and the bell icon so that you get notified every week when we release new videos. All right, in this video, we're going to solve the longest palindromic substring problem. And so what we're trying to do here is we're just trying to take a string and we're trying to find the substring that is a palindrome and also that is the longest palindromic substring in this string. And so in this example, we can see that ADDA is a palindrome. We also see DAD is a palindrome, although it's not as long as ADDA. And so our longest palindromic substring would be ADDA, or would be length 4 in this case. And so, as always, we want to make sure that we're properly defining our function. And in this case, we're actually looking for the string itself. And so this is a great example of where, just being clear of what we're looking for is key, because in a lot of these other problems, we've been looking at just like what is the number, so we would be returning this 4. But in this case, our function is going to look something like, we'll take in a string, and we're also going to return a string. And so the return for this would be ADDA and not 4. And so again, this is just why all these times we just want to be careful, because I can't tell you how many times as an interviewer I've interviewed someone and they just haven't done it right, and it just rubs me the wrong way because I know they weren't listening carefully, and it makes me concerned that when there are project specifications or anything like that at the actual job, that they're not going to pay close enough attention, and that there's going to be like merge conflicts and different things because they're not paying close enough attention. And so it's really important that you get this piece right. And so let's look at how we could actually solve this problem. So, the easiest solution, this is hopefully going to come as no surprise, but our easiest brute force solution to this is going to just be to look at all of the different possible substrings, right? We could look at all the substrings, and then we could easily write a function that would determine whether two strings whether a string is a palindrome or not, right? Because super easy way to do it is that if S equals S prime. So if S equals the reverse of S, then they're palindromes. We can also just do, count from the end of the string and the beginning of the string into the middle and say, are the characters equal? We can start in the middle of the string and count outwards. There are a lot of different ways that we can determine whether it's a palindrome. And then if we find all of the different substrings, we would just find B, we would find BA, we would find BAD, etc., etc. Eventually we'd find ADDA, and then we're basically going to say, is it a palindrome? And so we'd say, this one's a palindrome, this one's not a palindrome, this one's not a palindrome, and this one is a palindrome. And if we're tracking the length, then not too hard, right? So what's going to be the complexity of this, though? So finding all of the substrings is going to take us O of n squared time, right? Because we basically have a nested for loop. And then not only that, it's going to take us n squared time to identify each substring. But then for each of those substrings, we also need to copy it, right? Because we're going to need to make a copy of the string. It depends a little bit on what language we're using here. But for example, if we were doing this in Java, strings are immutable. And that means that if I say, s.substring, whatever it is, this is going to take me or if it's, I guess, I and j, this is going to take me O of j minus I time, which in the worst case is n, right? Because the worst case is that I is 0 and j is n. And so the worst case, when I'm doing this generically, I'm just going to say it takes me O of n time just to find the substring. And this is true for a lot of language. I think C is the main exception in this case, where C, it's, you're just using an array to back it. But if you're doing this in Python, I believe it's the same issue, where it's you're actually copying the string. And so you want to be very aware of what the time complexity is of that. And so what that means is that we have O of n squared different substrings, and then we have to copy each of them. And then we also have to determine whether they're palindromes or not. And so to determine whether they're palindromes or not, we're doing, it takes O of n time to compute whether something is a palindrome, and we have O of n squared strings. And so again, it's going to basically be this times 2, because we're going to have the same thing for computing whether they're all palindromes. And so we're going to get an O of n cubed time complexity here for actually doing approaching the problem this way. And so then, of course, the question becomes, how can we do this better? Well, let's look at our best conceivable runtime. So our best conceivable runtime here is O of n, because the best possible scenario is that we just iterate over the whole string once. We're definitely going to have to iterate over all the characters at least once, but we don't know whether we can do this problem by only iterating over all the characters once. And so that's our best conceivable runtime, so we know that we can at least strive for something better. And so let's think about this. Well, let's look at our Byte optimization here. So where do we have bottlenecks in this solution? Well, one of the bottlenecks is that we are actually finding and computing, or finding and storing all of the different substrings, right? And so that's a bottleneck, because that's taking us this O of n cubed time. And if we could get rid of that, then it's still going to take us O of n cubed time, because we then also have to compute whether all the strings are palindromes or not. But that's the other question we can ask, is do we actually need to do that? Do we actually need to be looking at all the strings and whether all the strings are palindromes or not? And the answer is that there's a lot that we can do to sort of limit our search to what is actually going to be a palindrome or not. And so I think that the easiest way for us to look at this problem is that, how do we know whether a string is a palindrome? And the answer is simply that we compare the characters on the left side with the characters on the right side and see that they match up. And what does that mean? So in this case, let's assume that we had the string A. A is a palindrome, right? Because it's a single character. And so the first, it's the same in both directions. And now if we added characters onto both sides, so let's say we put a B on the beginning and a B on the end, then is it a palindrome? Yes, it's still a palindrome as long as those characters are equal, right? And so we can add characters going out this way, and we can add characters going out this way, and as long as the characters are equal, then it's a palindrome. But as soon as the characters are not equal, then it's no longer a palindrome. And so in this case, we see that this is the palindrome. But we can do this. We can determine that this is a palindrome and determine that all of these inner strings are also palindromes by just expanding outwards from the center, right? And so this is the key insight here, I think, that with this problem and with palindromes in general, you can either go from the outside or you can expand from the inside. And so the point that the key thing to notice here is that, if A is a palindrome, then as long as these two are equal, that's a palindrome. As long as these two are equal, the whole thing is a palindrome. And we can keep expanding out until they're not equal. And so how can we apply this when we are actually looking at our string here? Well, it's actually super, super simple. It's a little bit tricky to code up, but it's simple in theory. And so all we have to do is just say for each character, let me try and expand out in both directions as much as I can. And so I'll copy the string here. We're going to start with the B. We're going to try and expand out, and we see that this is the end of the string, and so we can't expand out in that direction, so we're not going to expand out in the other direction here either. So we have B. We come to the A, and we try and expand out in each direction, but these are not equal. And so then it can't be a palindrome, right? And so we have A. We come to the D. We try and expand out in both directions. They're not equal, so we get D. We come to this D, and we try and expand out in both directions. They're not equal, so we get this. Then with the A, we see that we can expand, so we get a palindrome that's like this. And then with the D, again, we're at the end. And so that works if our palindrome is of an odd length. But now we also have to consider the possibility that our palindrome could be of an even length. And so what we do is we could do a second pass through here and essentially look for any time there are duplicate characters, right? Because if a palindrome is of even length, then the center two characters have to be the same. So we need two of the same character next to each other. And what we see is that when we come to this DD, oh, they're the same, so let's try expanding out in both directions from here. So, okay, now we get this length 4. And so the question becomes then, of course, what is the time complexity of doing this? And it turns out that in this case, our time complexity is going to be a lot better, because instead of having to go through everything so many times, we're really iterating over the whole thing once, and then for each character, we're doing at most O of n extra work, right? So we're doing O of n to iterate over the whole thing, or technically O of 2n because we're iterating over it twice, right, to find the pairs and then the individual ones, or the even and odd palindromes. And then we're expanding out, and the process of expanding out can take as much as O of n time, right? And so what we're going to do is we're going to have this times O of n, which gives us an O of n squared time complexity. And then in this case, you know, just looking, I'm trying to figure out, hey, like, is there anything better that we can do here? Is there a way that we could do this in linear time? And so I might take a few minutes to sort of look at this and see, you know, are there any bottlenecks? Is there anything that we can do? Really, you know, at this point, the bottleneck or the limitation is the fact that we have to iterate over everything and we have to explore all the palindromes, and I don't see a better way to do that. And so I would assume if I was solving this, that this would be optimal, even though, you know, this is a case where despite our best conceivable runtime being O of n, we're not actually able to achieve that. But so this is how you would approach the longest palindromic substring problem, and this problem also has a bunch of different ways that you can approach it. And I believe actually there is an O of n. There is an algorithm to solve this in O of n time, but it's not something that many people are familiar with, so it's not something that you would be expected to know in your interview at all. But this would be a good approach, and I look forward to seeing you in the next video. Thanks so much for sticking with me through this video. If you enjoyed this and are looking for more, you can check out our free 50 interview questions guide, where we go through 50 of the most common coding interview questions. And if you like this video, make sure that you hit that subscribe button and the like button. Let us know what you thought, and check out some of our other videos. We have a ton of other content like this, and I look forward to seeing you in the next video.